I am honored to have the opportunity to speak to you today about the topic of Box-Cox transformation data transformation from non-normal to normal distribution. This is a subject that holds great importance in the field of statistics. Importance of normal distribution in hypothesis testing. In hypothesis testing, the normal distribution plays a crucial role in determining critical regions and calculating p-values. Many statistical tests, such as the t-test and z-test, rely on the assumption that the data follows a normal distribution. Many common statistical tests, such as the t-test and z-test, rely on the assumption that the data being analyzed conforms to a normal distribution. The normal distribution is a fundamental requirement for the valid application of these statistical tests. If the data does not follow a normal distribution, the results and conclusions drawn from these tests may not be reliable or valid. Verifying the normality of the data is an essential step before conducting these types of statistical analyses.
Difference between normal and non-normal distribution. The normal distribution is a bell-shaped curve that is symmetric about its mean. The data points are clustered around the mean, with fewer data points at the extremes. The non-normal distribution lacks a clear bell shape and symmetry. There are more extreme outliers, with data points spread out more unevenly. The distribution is skewed and lacks the symmetry of the normal distribution.
Box-Cox transformation. The Box-Cox transformation is power transformation that is defined by y lambda, where y represents the data and lambda is the power to which each data value is raised. The transformation examines values of lambda between -5 and 5 to determine which value of lambda fits the data best, in terms of making the transformed values normally distributed. Some common values of the lambda are shown in table along with the transformation.
Optimal lambda is the value between -5 and 5 that minimizes the standard deviation, sigma, of the transformed data. In order to accurately compare sigma for different values of lambda, Minitab calculates standardized transformed values z for this comparison, according to the following formula, where gm is the geometric mean of the ny values. Two key data considerations for performing a Box-Cox transformation. All values must be greater than 0. If the data contains values less than 0, the Box-Cox transformation cannot be used. In that case, the Johnson transformation should be used instead. Secondly, data must be for continuous variables. The Box-Cox transformation is designed to work with continuous variables, not discrete or categorical variables.
The slide presents an example scenario where an engineer is analyzing lead time data for production jobs over a 10-day period. The engineer tracks the lead time for every production job shipped to customers for 10 days. After performing a normality test, the engineer discovers that the data does not conform to a normal distribution. Subsequently, the engineer carries out a Box-Cox analysis to assess the suitability of a Box-Cox transformation on the data.
How to validate normality of distribution. The test for normality is a statistical method used to determine whether a dataset follows a normal distribution. A histogram is a graphical representation of the data distribution. It can provide a visual indication of whether the data follows a normal distribution. Histogram is not suitable for small sample sizes, less than 100, as it may not have enough statistical power to reliably detect deviations from normality. Normal probability plot is another graphical tool that can be used to assess normality. The normal probability plot are suitable for both large and small sample sizes. Normal probability plot. A normal probability plot is a graphical method for determining whether or not the observations follow a normal distribution. If the data points form a straight line, it indicates the data is likely normally distributed. Deviations from a straight line suggest the data may not be normally distributed. Choose graph, probability plot, single. In graph variables, enter lead time. Click OK. Anderson-Darling test. One of the famous of normality test is Anderson-Darling test. The test is considered more powerful than other normality tests, as it gives more weight to the tails of the distribution, where deviations from normality are more likely to occur. It generates a normal probability plot and performs a hypothesis test to examine whether or not the observations follow a normal distribution. Null hypothesis is the data follow a normal distribution, while alternative hypothesis is the data do not follow a normal distribution. When p-value is less than 0.05, you reject the null hypothesis at the alpha equals 0.05 significance level and conclude that data do not follow a normal distribution.
Create Box-Cox transformation. Choose Stat, Control Charts, Box-Cox transformation. In all observations for a chart are in one column, enter lead time. In subgroup sizes, enter 1. Click OK. This plot helps identify where the minimum value of sigma lies. In the calculations, the actual minimum occurred at lambda equals 0.09. This is called the optimum lambda as it minimizes the variation in the transformed data. The Box-Cox plot contains two other lines, the upper confidence limit and the lower confidence limit. The range between the confidence limits contain the potential values of lambda that minimize the variation. The estimated value for the optimal lambda is -0.09. Because the rounded value of 0.00 is within the confidence interval, the engineer should transform the data using lambda equals 0.00. Use the confidence interval to determine whether a transformation is appropriate. For the Box-Cox transformation, lambda value of 1 is equivalent to using the original data. Therefore, if the confidence interval for the optimal lambda includes 1, then no transformation is necessary. If the confidence interval for lambda does not include 1, a transformation is appropriate. By identifying the optimum lambda and the range of acceptable lambda values based on the confidence limits, the Box-Cox plot provides a visual tool to determine the appropriate power transformation to normalize the data and stabilize the variance.
A transformation that uses lambda equals 0 corresponds to the log, original value. For example, log 13.86 is equivalent to 2.629. This slide shows a partial dataset of 100 data points, with the original data values and their corresponding transformed values using the log y. The probability plot for the original data shows a non-normal distribution, with the data points deviating significantly from the straight line. After applying a transformation, likely a Box-Cox transformation, the probability plot for the transformed data shows a much closer fit to the straight line. The transformation has effectively normalized the data distribution, making it more suitable for statistical analysis techniques that require normality assumptions. In hypothesis testing, the normal distribution plays a crucial role in determining critical regions and calculating p-values. The Box-Cox transformation examines optimal lambda value between -5 and 5 that minimizes the standard deviation, sigma, of the transformed data. For the Box-Cox transformation, a lambda value of 1 is equivalent to using the original data. Therefore, if the confidence interval for the optimal lambda includes 1, then no transformation is necessary. If the confidence interval for lambda does not include 1, a transformation is appropriate.